Hello everyone, myself is Dr. Lokesh. I am working here as Associate Professor in the Department of Physics, BMS IT and M. Today I am going to explain you about particle in a box. So it comes under quantum mechanics. So this is what a box here means. Here a box here means we are dealing with a potential box. So here I have created a potential well or a potential box of finite length L and having infinite height. So this is what infinite. And assume the potential inside the box is constant and you treat that as equal to 0. You know, since 0 is a constant number, so I am going to equate that constant potential to be equal to 0. And imagine outside the box or potential well, the potential is to be infinite. That means a huge potential is there outside the well. Now, in such a potential well, suppose if I take a quantum particle of some mass m, okay, then because of this constant potential, this particle will start moving with some velocity v, okay, and as it reaches this side of the wall, since huge potential is present, it has to rebound back. It cannot cross that side. And again, it will start moving with same velocity v. Again, after reaching this side of the wall, it has to rebound back. So it means to say that the particle is free to move only between the walls of the potential well. The particle cannot come out from this side by crossing infinite height, or particle cannot come from the sides of the wall because infinite potential is present. So now to this problem, now we are going to apply what is called Schrödinger wave equation. Okay, I hope you remember what is Schrödinger wave equation. So it is given by d square psi by dx square plus 8 pi square m by h square into E minus U into psi is equal to 0. So remember here, U is the potential, U or V I can call, and E is the total energy of the particle. Okay, now let us apply this condition to this Schrödinger wave equation. So this is called Schrödinger wave equation. Okay. So since inside the potential well, so what I have assumed? I have assumed U to be constant. Okay. And that constant I have taken equal to 0. No. Now let me put that here. So let me call as equation 1. So now equation 1 becomes what? D square psi by dx square plus, just put U is equal to 0, 8 pi square m by h square into E into psi is equal to 0. Okay. So let me call this term which is inside the bracket as equal to some k square. Okay. So what is k square here? So k square is 8 pi square m by h square into E. So let me call this as some equation number 2. Okay. So therefore now I am going to get this expression now, d square psi by dx square, okay, plus k square into psi is equal to 0. So this is my equation number 3. Okay. So if you remember, so in mathematics we have studied such an equation. So this equation is what is called a second order linear equations. And what is the general solution of any second order equation? So if you remember from your mathematics, the solution, okay, so the solution is what? Psi is equal to A sin kx plus B cos kx. So this is the general solution of So equation number 3. So you will come all this in mathematics. Okay. So where what is A? A and B are some constants. So which we need to evaluate later by using boundary condition. So let me call this as equation number 4. Okay. Now we are going to apply the boundary conditions for equation number 4 in order to get the value of A and B. Now to understand what is boundary condition here. If you see the diagram, the potential well here, see at x is equal to 0. X is equal to 0 means this end, okay. At this end, okay, since particle cannot be on that side, so we are going to say that wave function psi is equal to 0. Okay, this is called the first boundary condition. Similarly, at x is equal to L. X is equal to L means this end of the wall. Even that end also. So since particle cannot be there, we will write psi is equal to 0 again. So these two are called the boundary conditions of the particle. So these are called what? Boundary conditions. Okay. Now let us use these boundary condition to solve equation number 4. Okay. So what is equation 4? Let me write here. Psi is equal to A sin kx plus B cos kx. This is equation number 4, right? Now let me apply the first boundary condition. What is the first boundary condition? First BC, that is called boundary condition. So at x is equal to 0, the value of psi is equal to 0, correct? So therefore let me write equation 4. Equation 4 now becomes, so 0 is equal to A. So if I put x is equal to 0 here, sin 0. Sin 0 is 0, no? So A into 0 plus B. If I put x is equal to 0 here, I will get B into cos 0 is 1. So therefore, now I am going to get B is equal to 0. That means one of the constant in equation 4, this is found to be equal to 0 now. Now let us evaluate what is the value of A again by putting second boundary condition. So what is second boundary condition? It is called second BC. So again at x is equal to L, what is the value of psi? Psi is equal to 0 again. Okay. Now if you put that in equation 4, so equation 4 becomes what? Again 0 is equal to A. I will get now sin KL. I am putting x is equal to L now. Okay. Plus B into cos KL. Fine. But see already this B is equal to 0, no? We have found here. Right? So therefore what is now implies? A sin KL is equal to 0. Right? So this implies either A should be equal to 0 or what? Sin KL should be equal to 0. Remember, this cannot be 0. So this not possible. Okay, so what is the option here? Only this can be equal to 0. Okay, so that therefore I can now conclude sin KL can be equal to 0, right? So this implies the value of KL can be equal to 0 or pi or 2 pi, etc. Or in general, what I can write? KL will be equal to n pi. Okay. So this implies what is the value of K? K is n pi by L. Okay. So on solving equation 4, by applying boundary condition, like x is equal to 0 and x is equal to L? No, I could able to get the value of k as n pi by L. But remember, what is k square? According to equation number 2, k square is what? N square. Sorry, it is not pi square. Okay, so what is k square? It is 8 pi square me by h square. This is what k square we denoted, right? Now put the value of k square. So let me call as equation number 5. So from 5, if we substitute the value of k square, what I am going to get? So n square pi square by L square is equal to what? 8 pi square me by h square. Okay, so remember, I need to find a. So I have to simplify for a, right? So therefore, what is e is equal to? Now this e is equal to what now? N square h square by 8 L square. So remember, what is L here? Length of the potential well. Okay. And what about n value here? N can take values like 1, 2, 3, 4, etc. only. So these are called allowed values of n. Okay. So this is what we call as expression for, okay, expression for energy, okay, of a particle in one-dimensional box, 1D box. Okay, so remember how we got? We just solved Schrodinger wave equation and we arrived at this formula. Now, if I put n is equal to 1, remember n is equal to 1 is the first value allowed for, correct? No. Then what I will get? I will get the minimum energy as E is equal to what? Just put here n is equal to 1. I will get h square by 8 L square. So remember, this is the minimum energy and we call this as the ground state energy E naught. So this is called what? Ground state energy. Ground state energy. Okay. Next what? Next possible value is what? N is equal to 2. Correct? So n is equal to 2 means again I will get one more energy. E is equal to what? It is 4 h square by 8 L square. Okay. So this I can write as 4 times E naught. So this is what? The next energy which is allowed. So this is called energy in first excited state, that is called ES state. Similarly, if I put n is equal to 3, what I will get? E is equal to 9 h square by 8 ml square, and that I can write as 9 times E naught. So this is called energy in the second excited state. Okay, so this is called E1, this is called E2. Okay, and if we just see the value of E naught, E1 and E2, so it is either E naught energy or 4 E naught energy or 9 E naught. So this shows that energy are not continuous. So what is the reference? So this shows that energy, okay, values are not continuous. Okay. And what we call not continuous energy in quantum mechanics? Discrete, or energy is discrete. Okay. So that means, so if I apply Schrodinger wave equation to this particle, remember we have taken particle in a box, no? Potential well. So there is a particle which was moving inside this, right? Now as per this equation, the energy of this particle, that is E, is quantized. Okay? Thank you.